Okay. Is that working? Yes. Okay, just a few things before we kind of really get going. So on the, according to class schedule, there is supposed to be a magnetics quiz today, which I hope everybody studied for, but we're actually going to have that on Monday. However, to make up for that, so how there's just so many moving parts in this course, it's crazy. So there's a TBL. The TBL, there's a case history. I want you to download that. Okay, whoops, I didn't do that. I want you to download that and also complete the individual TBL for Monday. So that kind of gets that out of the way. And then you do the quiz, and then you do the same quiz with the TBL. So it's exactly the same as we had done before. And yeah, they need their laptop for this.
Yes.
Yeah.
We're gonna run the apps.
We'll run the app so that yeah, bring your laptop. The TBL, I'm not sure how many people have looked at it, but it's basically like finding a vertical pipe, and it's actually kind of a serious problem in some places. And it's very similar, very reminiscent to what you did at the beach where you're trying to find the vertical rebar. So I think you'll find that, oh, everything kind of fits together. Today, what I want to do is go over a few of the things that have to do with understanding how to work with such things, simplifying things from a dipole actually to a monopole. Anyway, so that's the schedule for this. And then the other thing, well, I could go to resources and GPG. There have been a number of people that have said, "Oh, gee, I would like to alter things." You're finding spelling mistakes on the GPG. The GPG is a work in progress, right? It's a huge work. We're trying to develop material so that it's easy for you to find things. It's easy for you to navigate. The material on there is correct and informative. And we'd like to get your feedback about mistakes that you find. Get your feedback about things like, well, that is not very clear. You know, really had trouble wording that, or if you had a diagram here, that would really help. Or if you talked about something, that would be really great. So there's two ways that you can contribute to developing this GPG. One is just through a simple discussion. At the bottom of each page, there's something here called Disquis. So that is an app that allows you to provide commentary about every page that's there. So at the bottom here, you'll find that there's a little cell that says Start the Discussion. You can simply click on this, and then what it'll do, it'll ask you to sign in, so you can use your Twitter account or your Facebook or your Google, anything, just to sign in on that. And then you can just go and type. This works on every page. So as you're reading through things, when you see things that like that's a spelling mistake or whatever, just let us know, put it down, and then we'll have a way of tracking it. So that would be greatly appreciated. There is another level where you can actually go in and use GitHub and make edits yourself and then do a pull request. We can discuss that later. But for now, just to capture the things that you sort of see instantly as you're reading through things would be great. So what I want to do today, I'm going to review just a little bit what we had done yesterday, Wednesday. So you collect data, and then you want to do some processing. There's two things that I said we would do. One is reduction pull, the other is upward continuation. I didn't really talk about this. I just sort of flipped through this slide. But what you're seeing here in the bottom section is data that are collected relatively close to the ground. You can see all of the information. There's a lot of ups and downs, and there's a lot of structure in that. That's fine. In fact, that's actually good because that's telling you something that you've got some good resolution there about what is going on. However, sometimes you want to look at the bigger picture, and you're just simply asking, well, instead of having this, right at the surface, what would this map look like if I was at some altitude? In this case, it's big. It's 5 kilometers. This is a really large data set. So if I looked at 5 kilometers, now I see I don't have all of this little ups and downs here. I don't have that higher resolution. I'm seeing more of a broad scale picture. And as I continue to go up, I do that. So the reason that you sometimes want to do that is for the following. If I take an object sitting up here, magnetize it, then I'm going to get, remember, I'm going to get a curve that sort of has a half width that's about equal to the depth of burial. If I bury this object more, deeper, okay, now it's got a lower amplitude, but is broadened out. Suppose that I actually had 2 of these things. So I've got this guy here, and I've got an object that's that's deeper. Then what I end up having here is the sum of this and this, and it kind of looks like that, right? So I'm basically sort of seeing this stuff that I'm closest to. If I then, however, looked farther up, this field falls off as 1 over r cubed. So if it's really close and it's got a high signal, so I can have a very small object. I have just real small, something that's close to the surface. It would give me a big signal and kind of mask out some of the other details here. However, if I went up in altitude and looked to see what this would look like, now the signal is going to fall off as 1 over r cubed, and eventually this larger scale body down here at depth is going to be the thing that contributes. So that's the idea. And then you can, again with the processing, you can take data on a plane, and then you can see, okay, what does that data look like if I go at higher altitude? And what you're seeing here as you go down is sort of the larger, more deeply buried structures that's connected with the Earth compared to stuff that's towards the surface and higher resolution. So that's the goal, and you'll also, generally when you see magnetic maps, they will tell you sort of what elevation they were plotted, and then sometimes you will also see what's called upward continued maps, and that's exactly what this is. Okay, so that's one thing that you will undoubtedly see. The next thing that we talked about was reduction to pull, and the idea here was that if you take an object and you vary it. You take the same object, you just vary it at different locations on the Earth. Okay, so if I vary it here, or vary it here, or vary it here, then I get 3 different pictures. If I vary it at the equator, my magnetic field looks like that. At 45, at 90. So those are 3 very, very different images, but it's just the same object. So if there was some way of converting this to a standard, and the standard is this, because if you've got something that's vertically magnetized, it gives the simplest picture, and so that's what we'd like to see. So the goal is to find some way of taking these data and making it into that. And that process is called reduction to pole. And it just requires some analysis to go from here to here. I'm going to show you, we don't have time, unfortunately. That's the really bad part about this course. There's simply not enough time to try to fit everything in, but there's an app that's being prepared now. It's a GeoSci app that allows you to import data, all kinds of magnetic data or gravity data, view it in different ways, and kind of make comparisons with geology and to make geologic inferences. I will show you that towards the end of the year once we kind of have a little bit more time to talk about things, but it's really cool. And I saw this morning the first image that came out of this that was obtained from importing all of the magnetic data over the surface of the Earth. So you can import all of the data. You can look at a particular section. We were looking at a section off of the west coast of British Columbia. You can see all of the faults. You can see the Juan de Fuca fault system come in. You can see the transition between the oceans and the continents. It is, just really cool. And then the fact that you can take those data and you can actually do some of these things. You can do reduction to pole. You can do a upward continuation. So you can actually sit down and work with this. And the reason that we're developing this, and this is a joint MDRU GIF project. It's going to be presented to the general public in about 2 weeks downtown at the facility there. It's just to allow geologists to have a more in-depth conversation with geophysical data and to get some more stuff up. So you're going to see that, but we don't have time. I want to take you on just some aspects about interpreting the data, and in particular, I want to talk about understanding how structures would be observed by the use of magnetic charges. That's going to be very important when you work with the data that you collected at the beach, because we're going to see that you could interpret the magnetic anomaly just as if there was a single point magnetic charge at depth, and then that opens up scope to understanding what you're getting. So I talked about these, here's dipoles that are obvious for UXO, and you can see that they're remnantly magnetized. If you're going to try to work with these kinds of things, then you're going to parameterize, let's say, the object just as a magnet, and then you're going to try to find the parameters like the depth of the center of the magnet, the orientation, and the strength of the magnet. So that's one way of trying to get some additional information out. And the whole process of doing any kind of parameter estimation is one in which you have an ability to take the object, simulate the data. So in this case, we've got, say, UXO, you simulate the data, and then that gives you something that looks like this. And then, again, you want to do that inverse problem of trying to find the parameters of this object that gave rise to those data. So that's a bit of an inverse problem, but it's also something that's really doable. And here's an example of that, and I show you this for a couple of reasons. So here was the initial data, and then you go ahead and you do that parameter estimation, and you get these numbers that are out here So easting, northing, and depth. So now that's giving you some very specific information about what's there. And also remember, have the moment. So that was the strength of the magnet. And then you've got the orientation of that magnet. And you have the predicted data. So here's the data. And the predicted data, here's the observed. You look at the residuals. You get something that looks like that. So it's not bad. There's still little bits of stuff maybe around. But you've actually done a pretty good job at fitting those data. And the parameters of interest then tell you something about what you're looking at. So I now want to talk a little bit about simplified techniques of kind of working with charges. So I remember we kind of did this right at the beginning. If we have a magnetic charge Q, okay, and then we look at the magnetic field that comes from that, then if we have a positive charge, then the magnetic field just comes out cylindrically or spherically from that in this kind of a pattern. So that's what you'd have if you had a positive charge, and a single charge is called a monopole. That's where that comes from. Monopole, single charge, same thing. If you had a negative charge, then it kind of comes in like this. So those are the two things that we've talked about before. We have a positive charge, field goes out, and in that case we call it the North Pole. Field goes around to the South Pole where you have a negative charge. And the magnetic moment of this sort of couple is related to the charge, the distance between the charges divided by mu naught. So that's the magnetic moment. And then here was that formula for the magnetic field of a dipole. Just one kind of comment about this. If we have a magnet here, a magnetic moment that's pointing in this direction, so it's like this, and then if we look at the magnetic field at a value of theta is equal to 0, so now we're sitting right up here. So this is a case you're going to be interested in a lot. You've got a vertical magnetized body or dipole. You're sitting right up here. And then the strength of that field, okay, is obtained through this formula. So if theta is equal to 0, this term goes. And then all you're left with is something that looks like this. So this quantity here times 2 cosine theta, but theta is 0, so that's 1. So at the end of the day, the magnetic field, so if you're sitting up here, is equal to mu naught m over 4 pi r cubed, and then it's times 2. That's what's up here. If you're at theta is equal to 90 degrees, so in other words, if you're at this angle here, so if theta is equal to 90, you have this term. So now you're sitting here on the Earth. So now here all you just is not m over 4 pi r cubed. So here's the magnetic field going like this, and here's the magnetic field going out like this. So notice that this is a factor of 2 more than it is here. So the field at the equator is only going to be half the field that you have at the pole. And if you remember when we looked at the magnetic field of the Earth and those pictures, we saw that it was really high up here, sort of like 60, 70,000 nanoteslas. Down here it was low, it was more like 25,000. So all of that kind of fits together, right? So we've got an equation, kind of tells us something about how things operate at the poles and equators, and we've got these different charges that can make up a dipole. So let's kind of think about what happens if you have a uniform magnetic field that comes onto a body. And it's kind of described here. So suppose I take a a uniform body. So let's just take a prism. So here, like that, and I put a magnetic field on like this. Okay? And now think about each of these, this guy being divided into a whole bunch of little blocks, okay? Okay? And so I can think about kind of carving my earth up into a whole bunch of little elements. Okay, and now I'm going to take this, and I'm going to say, okay, what am I going to observe here? Remember, each of these guys, excuse me, you guys, see any questions or something? Okay. Each of these guys is like a little magnet in itself, so I could think about him kind of lining up like that, so he gets magnetized like this, okay? And then simply this guy here, he could get magnetized like that. But notice how we think about this. At the end of this magnet, you've got like a negative charge here, and this is positive, but then this is a negative charge, this is a positive, this is a negative, this is positive. So it's kind of like these guys sort of cancel out. And at the end of the day, your effective charge is just sort of a negative at the top and kind of a positive charge at the bottom. So that's what I'm trying to kind of describe here. You've got a magnetic field coming down on something, and then everything kind of gets magnetized in that same manner. But then, you know, the pluses and the minuses of those guys kind of cancel out. At the end of the day, you're effectively just ending up with a charge that's negative at the top and positive at the bottom. Okay. The strength of those charges is equal, we use a symbol tau, and it's the dot product, of the magnetization to the normal vector. The normal vector is the outward pointing normal. So if I take something that looks like this, and so these are, this is the here's the magnetization, it's coming down, down like this. The outward pointing normal is like this. So M is pointing this way. Dot and hat, okay, is going to be equal to some negative value times some number, okay? So by thinking about how the fields are coming in, how everything is magnetized, we end up that we can see that, oh, I've got a negative charge here and a positive charge here. And it turns out that's all you need to know. So you can then compute the magnetic field at any point out here just by looking at the effect of all of these negative charges and by the effect of the positive charges. You don't have to think about, you know, working with each of the individual cells. And that's why this is so important in a way, and it's so simplifying. So long as you have a body that is uniform susceptibility, then at the end of the day, we can think about the magnetic field that we're going to get as just being the result of the fields of all these individual charges. And because we know what the field of a charge is, we just have to sum them up. So that's a cool concept, and where it's going to play a role big time for you is going to be in your pipe problem. Yeah?
So M is just perpendicular to the surface that you're looking at, which is being magnetized?
Correct. Okay. So if I have let's say a shape that looks like this, okay? And now so if I have a field that comes in like this, and now so here's my magnetization, looks like that. And is this here? So along this side here, M dot M is going to be negative, so I'm going to have a negative charge on here. And out here, okay, M dot M is going to be positive, so I've got that. So that's why this is just such a huge simplification, especially when you've got, you know, particular geometries, because instead of thinking about, oh, I've got to add up everything that's going on in the middle, I just simply look at where I've got the surfaces and see how the magnetization interacts with that normal. Okay, is that kind of clear? Because this is kind of an important point. Because now here we come for your problem of either finding the pipe, which is that's what you're going to do in the T-based learning, or you're on the beach trying to find the rebar. So here's the scoop. So here's your pipe or rebar. It's got a radius A. We have a vertical field coming in, so it's magnetized in this direction. So the magnetization is just going to be equal to the susceptibility times H naught. So that's this guy here. And then tau, the charge, is just m dot n. And the only place that this is going to be non-zero is at this end and this end. Along the sides, m is this way, the outward normal is that way. So if I have a pipe that's coming in like this, so the magnetization is like this, but the outward normal is like this, okay, it's 90 degrees, so m dot m hat is equal to 0. So the only place I'm going to have magnetization is at this end and that end. Now, we can now get a total charge here because we know the charge, that's the charge density, so it's charge per unit area, charge per meter squared. So if we multiply by the area, pi h squared, we get the total charge. So long as I'm sitting, at least a radius or two away, this whole problem is going to collapse to something that's effectively just got a single negative charge Q here and a positive charge Q. So now it's really simple, right? Because now your magnetic field, so you're sitting up here, okay, with your magnetometer. We've got some rebar or something that's buried in, some pipe, okay, sitting in like this. And effectively, we just have some charge here that looks like this. And so the magnetic fields are just coming in like that, and they're varying as 1 over r squared, which was the formula just for a single charge. So you take what you have considered to be a moderately complicated problem, looking for this pipe or something like that, and you reduce it to the point where it's like, oh, I've just got a single point charge here, and now I know what to do. So this is going to form the heart of your analysis for the lab, as well as for the team-based learning and case history. So it makes it simple, but at the same time, you're still using a lot of the elements that are involved in the whole magnetic process. So if you've got some negative charge here, here's the fields that are coming in like this. And now remember what your total field anomaly is. Your total field anomaly is this anomalous field that you're getting here, dotted into the direction of the Earth's field. And in this case, you'd expect to get something then that looks like that. So that's going to be your profile kind of over the top of your. Okay. So you can work with that. I'm not going to fire up the app, but the app has actually got an ability to work with a negative charge and a positive charge and to actually separate them. So this gives you a lot of really kind of interesting things to play with, because you can do experiments where the different distance between here and here is very small, in which case now it looks like a dipole, right? And so if I have if I've got a negative and positive sitting down here, now I've got effectively just a dipole kind of field. Or if I pull this guy way down, then now I'm just sort of seeing fields that are coming in like this. Effectively, I'm just sort of seeing what's happening in close here. So I've got fields that are coming in like that. There's no curvature. So you can have a chance to kind of play around and experiment and see, okay, what happens if I have a short pipe? What happens if I have a long pipe? How's that all going to affect what my data look like? And yeah, you can kind of work with the app and ask some of those questions. So that's kind of the thing that we have at this point. The other is actually working with complex bodies, and that's where the process of inversion comes in. And I think the thing that I wanted to just re-emphasize here is that the one thing about magnetics is that the principle of superposition holds. In other words, if I've got a couple of different objects here, then the field that I'm going to measure at the surface is going to be the fields from this object by itself plus the fields of this one, etc. So here, if you've got a single prism, it looks like that. But if you've got 5 different prisms, now you can have a more complicated picture, and it could look like that. But the principle of superposition says that I can build this picture up by looking at the effects of each of these images. And that means that, the data can become more complicated, and then to actually go ahead and work with it, we're going to have to invert it. So here's an example. This is a mine in northern Quebec. It's called Raglan. And one is interested, so these are magnetic data, so you see that there's positives and negatives. So some of it's been mined, and there's other zones that need to be mined. But there's an area in here, okay, that you could take these data just by themselves and work with them and do this 3D inversion. So here's what the data look like. And then you go ahead and you do the inversion. I'm not sure where that went, but it kind of comes out to be looking like this. So here's your data, which is kind of interesting. It shows that there's something positive, there's something happening here and here. So there is magnetic material. And this particular example is kind of interesting because it's one of the first examples that was actually done for using 3D magnetics inversion. And it helped solve a problem because there was a controversy among the geologists and the geophysicists at that point about what the fundamental mineralization system was for this region. The geologists had thought that the mineralization was just kind of coming up in cylinders, something like this. And the geophysicists were feeling that wasn't consistent with the data. So the geologic description here would have been that you've got some kind of cylinder of magnetic material coming up here, and maybe another one over here. The geophysical inference was that now it looks actually like these things are connected at depth. So that's a big thing, right? You've got a geologic concept for what's going on, and that affects how you do your ore reserves. It affects how you're going to do your drill program. It affects everything. So if that is not correct, then it can really change things. So what was done here was to take these data, do a 3D inversion, and now you end up with something that looks like this. So there certainly is magnetic material that's kind of coming up at one end, and there's also magnetic material that comes up at the other. So this part in here kind of corresponds to that, and this part in here corresponds to that. But what you see is that magnetic material seems to be connected at depth. So it's almost like, so instead of a cylinder here and a cylinder here, it was like it was some kind of a U-shaped continual mineralization that kind of connected these things at depth. So that's what it looked like. That's the geophysical image. And then, to support or refute that, then they drilled a drill hole here. and they got substantial amounts of magnetic material as well as mineralization. So that actually showed that that these things were connected at depth, and then it completely changed the geologic model that they had for the solar system. So just a couple minutes then to flip through a few applications. So I come back to this slide here, and again, this is how you need to formulate the problem. So the first thing is really addressing, okay, what is the problem that I want to have solved? And then that connecting thing is what physical property, in this case it's susceptibility. And then that fits over to the geophysics side where you've got development of the survey, the data, processing, version. Do that, and you come back here and you have a physical property model, and then the engineer or the geologist can look to see how that impacts. So that's the general framework, and as we talked about in the first couple of lectures, we're going to set all of that up kind of in a 7-step framework where you first of all ask your questions, figure out the property, which survey, what data, what processing, what interpretation, and then some synthesis, like, okay, how have you impacted? So there's a number of examples. I first want to show you maybe something just from the data images. So here's a question about trying to do geologic mapping over a particular region. So there's some places where the rocks are outcropping, but also you've got really vast spaces to be looked at. And really what you'd like to do is to be able to take this and convert it to different geologic units. So maybe all of this is unit A, and this is unit B, or maybe they're cross-country. So it takes a lot of effort and time and money to go out and actually physically walk the ground and map everything. And hence, the reason for geophysics, especially magnetics. Because magnetics is probably one of the cheapest geophysical surveys that can be done. And it can be done on like regional scales or smaller scales. And it's particularly because you can fly these things. So it's really easy. I showed you examples before how you can mount magnetometers on various aircraft. And now they're starting to get more into drones too. So we're going to hear a lot more about that. I guess the other thing is that you're often really based on, for the geologic understanding, you really want to know things about the shape and the contacts. So contacts are always really useful things, especially for mineral deposits. And here again is where mapping with magnetics can be really useful. I showed you this briefly before, but I think maybe we could do it again because there's more insight. So the area here is, so that's 30 kilometers by 30 kilometers, so size. And this is a magnetic map. So now these numbers are meaning more to you. So this is 329 and minus 168. So maybe the first question is, if somebody showed you that, is there any place, that's the question. The scale of these numbers, okay, are these numbers that could have been measured by, let's say, the instrument that you had at the beach, where you had a total field magnetic value? In other words, could these be total field magnetic values, just as measured? Anybody? Yes?
No, because total field would be like 64,000 or much bigger.
Right. Yeah. So on the Earth, measuring the total field, there was nothing under 20,000. Up here, we're at 50. So that means that these data must have been reduced somehow. And generally what you do is you subtract off, the Earth's magnetic field at that particular point in this region. And I don't think I mentioned explicitly IGRF. Did I? It should be in the GPG. The IGRF stands for the International Geomagnetic Reference Field. So it's something that you look up and you can find out where what the value of the magnetic field is from a global perspective, where it is at any particular point on the Earth, and also how that changes. So that's something that you could go to and find out what the magnetic field values were, and then so that would just be some number, and you subtract that, and then you get some positives and negatives. Okay. The next thing is just like, okay, let's just look at this as an image. Here's the geology map, and then here's the magnetic image. And you can just see by looking at these things, all of the different correspondences, in particular, let's say, stuff that's coming in like this. And the power of the geophysics is that if you had a geologist that had gone out and mapped this as some particular unit, and you recognize that, oh, it's got a magnetic signature like this, then you can infer that all of this sort of might be the same unit. So you use the magnetics as a proxy for a particular geologic unit, and then you just follow along, and then you could go out and map some areas that are kind of interesting on the basis of that, and just sort of see how well you do. So that is probably one of the biggest uses of magnetics from the point of view of geologists, so just simply to look at the data and use them to make geologic maps. Faults are a big thing, or dikes or fracture zones, because then you often, either two things happen. You either get magnetite destruction that is going on. So if you've got some kind of contact or fault in here, you can get magnetite destruction, and that changes the magnetic signal from this side to that side. So in here, for instance, there was a map fault. If you look at the magnetics in here, you see that it kind of comes out. So that's a very valuable thing in trying to get information about the structure. Ore deposits. Here's another example. So ore, iron, has got a great big magnetic signature, and here's your anomaly. You get a good sense of where you might want to think about for doing field observations, and just provides a lot more information than just simply looking at what the topography is from a satellite. You can do a number of different kinds of processings with this, and this is what that GeoSci apps would be, because, well, here's a couple of things. So here's a Landsat image of an area, and here's the topography. So those are two images. And here's the surface geology. Okay, so you can see what correspondences or not there are between these guys and surface geology. If you now go ahead and you do the magnetic data, so here's the magnetic anomaly map. So that's what we've been talking about so far. But in addition to upward continuation and reduction to pole, there's a lot of sort of image processing that you can do with this map. So for instance, you could do something like finding how rapidly the field changes if you go up in height. Remember, we could do upward continuation. So that means I could tell, how much, if I went up 10 meters, what the change would be. So I could plot that. It would be like a vertical derivative. And here's a map of that. So it shows, first vertical derivative. And again, you see their structure, and you see that there's difference. There's differences here compared to here. Then we could use a tilt angle, another process, and again, it gives us a different picture. So the idea is that you take one set of data, and then it's just a picture, and then you can do a whole bunch of different things with it. Just like the same, yes, as you do with your camera. You got a photo of something, and you've got little image processing things, and you can lighten this or darken this, or try to find edges or whatever. The same as you can do with geophysics, and there's a whole host of these things that can be done. And each of them gives rise to a different picture. And some of those pictures might actually contain information that you want to have. And again, if you look at the geology over here, if you look at this particular unit here, you can see he's kind of showing up here, he's showing up here, he's showing up there, but in slightly different ways. And there's different scales of information that are coming in here. So I don't know in this particular case what might be really useful to the geologist as he's looking, but there's stuff there. And I think that's the essential. And to be able to have tools, which is what that app is that we're doing, to take this picture here and generate this picture, or generate this picture, and look at the geology, useful. Yeah, I mentioned looking at small objects and trying to see what we could do with them. I just thought you might be interested in this. Do you realize that just within North America, there's like 3,000 sites, that are contaminated by military bombs and different kinds of ordnance items. So every time, even though Canada has not really been at war, the United States has not really been attacked, they've got all of these proving grounds in which they train people on how to use the weapons and do things like that. And so the result of that is that there's a lot of munitions that are buried at various places around the world. And the cleanup cost on these things is absolutely horrendous, because you have to worry about safety issues, and it's very labor intensive. So here's, just to kind of put it in perspective, these are all old military proving grounds in the United States. There's Lowry, Colorado, Fort Ord, California, Erie, Ohio, up in the north, Amchitka, Kaho'olawe in Hawaii. All of these places have been training places for Army and Marines. And then you have this munitions problem. Because now you're going to go in there and you think, well, magnetics, that could really be useful, right? Because the ordnance items that we are magnetic. But then there's always a lot of other stuff that's done. So here's actually munitions that are live, but you could have fuse caps, or you could have a horseshoe. Right? So there's going to be a problem there in really distinguishing. You do find something, whether it needs to be dug up or not. And so then the question is, well, how do you find these things? And a magnetometer is the way. I just wanted to show this. This is kind of an analog magnetometer. What this guy is doing is just going over the ground. He's got some earphones on, and whenever it hits anything magnetic, it gives a little buzz in his ear. And then he whips a flag out of his back pocket and he plants it. And that is then a location in which there's something buried, potentially a UXO. Here's what it looked like at the end of the day. You look at this stuff and it's like stuff all over the place, right? So now you can imagine if you had to go and dig this stuff up, it would be really complicated. The other option is to come through with digital, modern systems here. So here's 4 magnetometers that are going through. You can't see anything over the grass, but then you go ahead, collect the data, and you get that particular picture there. Yeah, so I guess that's about all we have. There is a couple things with respect to good data and bad data. And I might be able to come back. You can sort of flip your way through here. Hopefully we can kind of get back to things maybe towards the end. So what we're going to do on Monday is, download that TBL, do the individual TBL, so fill that out, and that gets marked automatically. And then we'll have the TBL quiz, and then you do that with your team, and then we'll do the case history.